There is a giant hole in the universe that leaves us wondering about our cosmic address. Imagine a big, empty ball measuring 2 billion light-years across in every direction. It would take half the age of planet Earth for light to travel from one side to the other. Right here, in the very center of this cosmic void, sits you and me. Our entire Milky Way galaxy calls this massive, underdense region its home. The idea that we live in the middle of a huge hole might sound a bit terrifying. There is a strong chance this hole is our key to understanding the universe. When we look up at the night sky, we never quite see the full picture. Even from the darkest place on Earth, our view remains entirely restricted. Powerful telescopes in space reveal that the universe is not an endless blanket. The real universe looks like a vast three-dimensional structure of voids and clusters. Cosmic filaments and walls stretch out like an infinite web across space. This network looks surprisingly similar to the way neurons move through your brain. Such a striking structural similarity is probably not just a simple coincidence. Two opposing forces work constantly against each other to create this cosmic web. Those two major opposing players in the universe are gravity and dark energy. Most of us are already pretty familiar with how everyday gravity works. It is the exact reason why things fall down when you drop them. Gravity is fundamentally a product of mass and physical presence. The Earth is very massive, creating the steady gravitational pull you experience now. Even astronauts floating in space are still caught up in Earth's gravity. The Moon is also trapped by this pull, which keeps it close. Gravity can stretch out across vast cosmic distances over millions of years. The more massive an object is, the further its reach can extend. That is how the Sun's gravity holds onto planets as far away as Neptune. The most massive object in our galaxy is a black hole at the center.
It is formally called Sagittarius A star by modern astronomers and scientists.
This object is not a traditional star, like the one warming our planet. The star label actually refers to an asterisk used to mark its importance. Saying Sagittarius A asterisk out loud can feel pretty awkward and clunky. So, researchers simply use the word star to keep things conversational. The gravity of the Milky Way holds our sun safely in place.
Yet that same gravity is powerful enough to reach out toward other galaxies.
Our closest major neighbor galaxy is the magnificent Andromeda system.
Andromeda is stuck right here inside the same giant hole with us.
One thing you might find comforting is that we are not entirely alone.
The Milky Way is part of a larger cluster called our local group. There is a large spiral galaxy called Triangulum, located a bit further away.
A few dozen much smaller dwarf galaxies also cluster closely around us. The combined gravity of these three large spirals is remarkably strong. All three of us are being slowly pulled together into one epic collision.
This massive event will eventually merge the spirals into a single supergalaxy.
That grand cosmic merger is still 2 or 3 billion years away. Therefore, you do not need to worry about the collision anytime soon. The inevitability of this merger does create a fascinating scientific problem to solve. If galaxies have a natural tendency to pull themselves together into clusters, why? How did we end up with a giant void where hardly any galaxies exist? Were we somehow rejected by the other massive galaxies in the cosmos? Could the Milky Way and its neighbors be the ultimate cosmic misfits? To find a more reasonable answer, we must examine dark energy closely. Dark energy sounds like spooky science fiction, but it is a real label. It describes the mysterious force causing the entire universe to expand outward.
When thinking about exploration, people usually imagine rockets, satellites, and distant planets.
However, some of the most fascinating discoveries happen much closer to home. That brings us to our sponsor, RadioCode, a modern portable radiation detector.
This handy device lets you explore and visualize radiation all around us.
Radiation is completely invisible to the naked human eye under normal conditions.
What makes RadioCode impressive is its ability to measure radiation extremely fast.
It operates up to 40 times faster than traditional Geiger counters do. The device also helps identify specific isotopes through detailed radiation spectra analysis. It connects seamlessly to free iOS and Android applications for mobile use. These apps unlock advanced features like search mode and accumulated dose spectra. You can view spectrograms and interactive color-coded radiation tracks of your travels. Whether exploring cities, forests, or old mining sites, it provides new perspective. They also offer a wide range of practical accessories for custom setups. Get 5% off all RadioCode devices and accessories using code SPACED026.
Just head to radiocode.com or use the link in the description below.
Start exploring the invisible world of radiation right around you today.
This brings us back to one of the biggest puzzles regarding cosmic gravity.
If mass attracts other mass over long distances, everything should collapse inward. In theory, all matter in the universe should be pulling itself together tightly. Instead, we have clear evidence that the universe does the exact opposite.
Space is continuously expanding outward on a massive grand scale.
More recently, scientists noticed that the speed of expansion is actually accelerating. This means dark energy is not just a passive opposite to gravity. It is a more powerful force, pushing objects away from each other faster. Just as gravity is powered by mass, dark energy appears powered by emptiness. The smartest minds on Earth are still trying to figure out how this works. But we know for a fact what the macroscopic result looks like today. If two massive objects are close, gravity pulls them toward each other. If two objects are very far apart, dark energy pushes them away. The crazy thing is that this cosmic struggle started with the Big Bang.
Knowing this details about the ancient universe seems almost impossible to achieve.
Yet we can actually show you a picture from 13.8 billion years ago. That snapshot captures the universe roughly 4,000 years after the Big Bang. Scientists call this remarkable picture the cosmic microwave background, or CMB.
It represents the oldest light that human instruments are able to detect.
That ancient light is so old and faint it fell below visible spectrums. It sits below infrared radiation, all the way down into microwave frequencies.
The early Big Bang was not actually painted in yellow and blue.
It was never shaped like a flat, oval map of the world.
This visualization is a two-dimensional representation of a complex three-dimensional image.
Colors were added artificially to show tiny differences in early cosmic temperature. Red colors represent hot spots, while blue areas show colder regions. These temperature variations directly correspond to areas of higher and lower density. One of the most intriguing parts of the CMB image is down here. This specific region is widely known to astronomers as the cold spot. It might not look like much due to its two-dimensional projection placement. However, it is a massive region where ancient light is significantly colder. What makes this spot truly stand out is its unusual surrounding environment. It is bordered by regions that are noticeably hotter than the cosmic average. This creates a massive temperature contrast in one single localized space. Researchers compare it to falling off a high mountain cliff into a valley.
No one is entirely sure how such a strange anomaly came to be. Theories range from a deep supervoid to an imprint from a parallel universe. What it proves for sure is that powerful forces shaped early creation. That is how we ended up with a universe full of complex structures. Pockets of dark energy expand into voids, while gravity pulls galaxies together.
This means there is a natural opposite to every major cosmic void. Those massive destinations are what scientists define simply as cosmic attractors.
This destination is ultimately where our merged supergalaxy is heading. The good news is that our combined galaxy will not stay stranded forever. We are currently being pulled steadily across space by outside forces. The mass of galaxies outside our hole is drawing us outwards steadily. Even those surrounding structures are being pulled toward an even greater force. Every single galaxy in our general area of space is moving now. They are being reeled in like a fish on a line toward one point. That monumental destination in the cosmos is known as the Great Attractor. As with many things in deep space, its exact source remains mysterious. We can confirm there is a major gravitational anomaly near our local hole.
To power this massive flow of galaxies, it needs staggering amounts of mass. Its concentration of mass is roughly 10 quintillion times greater than our Sun. That staggering number equals about 10 million billion suns packed tightly together.
The main problem with studying the Great Attractor is our viewing angle. Even though it is humongous, we cannot see it directly from Earth.
That visual restriction happens because our own Milky Way galaxy blocks the view. The dense core of our galaxy covers about 20% of the sky. This obstruction makes it extremely difficult to observe what lies beyond it. Astronomers refer to this blocked region of space as the zone of avoidance.
That hidden zone is precisely where the mysterious Great Attractor lies today.
This stark contrast between empty voids and massive attractors shapes our universe.
When we look at the bigger picture, space is full of holes. The universe resembles a giant sponge or a piece of Swiss cheese. The most infamous example of these deep voids is the Boötes void.
It is frequently nicknamed the Great Nothing by astronomers and science enthusiasts.
This region provides incredible perspective on our own modest place in space. Spanning 400 million light-years across, Boötes is exceptionally deep and dark. Based on average cosmic density, a region this size should contain galaxies. It should hold about 2,000 galaxies under normal circumstances.
Instead, the Boötes void is home to a mere 6 galaxies total.
That represents an astonishing amount of empty, lonely space in the universe.
When we compare that to our local hole, called the KBC void, differences appear.
Our local hole is not anywhere near as dark as Boötes.
As with most things in science, this realization is all about relativity.
The KBC void is much larger than Boötes, but far less empty. This massive structure is made from hundreds of thousands of interconnected galaxies. Therefore, our void is better described as an underdense region of space. Depending on where you look, density is 20 to 80% lower. We are not isolated in a desert. but resting in a galactic suburb.